thanks for having me. Again, I'm Jim Thomason. I manage our imagery and analytics products at Planet. And I saw from the raise of hands that not everybody knows what Planet does, but those that do, you might be wondering why a satellite imagery company would be at an AI conference. And we, like so many others, run into the need as we look at our kind of global data set to leverage tools that only machine learning and AI can help us solve. These are the tools that help us achieve our overall mission, which our mission at Planet is to image the entire Earth every day, and from that imagery to make change visible, accessible, and actionable for us and our customers to use to make a difference. So when Planet first started, we thought this was just going to be a bit of a hardware and mission control challenge, and it was. And we created some really high-functioning satellites in the process. But we also had to build some first-of-its-kind automated mission control to achieve this as well. So this video shows a little bit of what goes into imaging the whole Earth every day. So we have a fleet of our nanosatellites, what we call SuperDoves, and these are 3-meter resolution. They're in a polar orbit over the north and south poles, and anytime they're over land, they're imaging, just pointed straight down, scanning the whole Earth. We have our SkySat fleet, which is a high-resolution satellite, and this shoots at 50-centimeter resolution. So when we see change in the medium resolution, we can zoom in and get a closer look. So there's 15 of these SkySats in a similar polar orbit over the north and south pole. And then we launch some in an inclined orbit. This is that diagonal line you see going across the Earth. What that does is it gives us the ability to zoom in and take a look many, many times a day. So 10, 12, 15 times over a single location. To give you a sense of what this looks like on the ground, these are the large footprints of those medium-res images, and this is the scan of the whole Earth. When we see change, you can zoom in and you get this smaller footprint, but much finer grain detail, so that you can see exactly what is happening on the ground. So we've created a bit of a problem for ourselves, and we can't stop. We want to build more. We've built this constellation, and we bring down 30 terabytes of data every day. We also have a license. We're heavily regulated by a bunch of people, and they say we can't delete any of our data. So we have 30 terabytes that we add to our archive each day. We can't get rid of it, and it takes a whole bunch of processing to make heads or tails of it. In addition, we want to build more satellites, right? Because that's kind of what we do. So we have a next-generation fleet coming. You saw our SuperDoves in the last animation. In this imagery, you see things like buildings and roads, and you can see bodies of water and forests and different land cover. Our high resolution, the SkySats, you can see vehicles, things that move. But we want to build some new stuff like Pelican that you see in the bottom of the screen here. This is our next generation, very high resolution satellite. And so this is 30-centimeter imagery. And so you see even more detail. And we're going to launch more of them. We have 30 that we're going to put in space. And so this is going to give us 15, 20, up to 30 images of every point on Earth. We also have a hyperspectral sensor. We just announced the other day, we named it Tanager, because we like to name things after birds. You should look up a tanager bird, they're beautiful. And this is a hyperspectral imaging satellite, 400 spectral bands, which some of you may not know exactly what that means, but we have 400 individual unique slices of the electromagnetic spectrum, not only in the visible part, but more interestingly, as you go into parts of the spectrum where you can see methane, you can see CO2. And this gives us the ability to do kind of chemistry from space. But again, this is just creating a massive amount of data, and that's only Planet. Another remote sensing data provider is the European Space Agency. You can see here their roadmap of kind of past, present, and future spacecraft, and they're generating from one of their programs called Copernicus. They generate 20 terabytes of data every day. And so for those of us that want to understand the Earth, those of us that want to look deeply at change and understand why and where it comes from and what we can do in response to this change, we've created this massive data problem. And we run the risk of complete data overload. We've created these archives, we've created these data sets, so we can answer just about any question we have about the Earth around us. But we haven't equally generated all the tools and capabilities to make heads or tails of this data. So a lot of our customers who want to use planet data, they want to use Copernicus data. That's a 50 terabyte data set each and every day. And when you talk about things changing on the planet, you're looking at years and years of data. So 50 terabytes a day over many, many years, you start to see the scale of this problem. So for me, kind of working on the product side, I want to make sure that we're leveraging every tool available to us, and we're giving every tool available to our customers to work on this problem. And for me, I think that one of the critical components here is using ML AI technology to do sensor fusion. And only through this ability to fuse many, many sensors together into one data set that is easily to analyze and easy to extract insights are we going to be able to really make heads or tails of all this data. So this is kind of one slide view of what we do at Planet, kind of on the back end. Some of you that aren't familiar with satellite imagery, we talk about it in different processing levels, level 0, level 1, level 2. So you can see on the left side of what I like to think is a bow tie, you get these sensor data. Level 0, really raw, unprocessed imagery. It could be imagery, it could be radar data, hyperspectral data that I talked about. And we bring all these sensors in on the left side, and most of what our processing is doing is combining these sensors, putting them into a more common format and a more harmonized state so that we can then create a smaller number of analysis-ready data sets, this nice knot in the middle of the bow tie, this level 3 kind of sensor-agnostic thing. And once we get there, you can then analyze the data like any data scientist, right? You don't have to be an optical expert. You don't have to be a satellite imagery expert or a radar expert. If we do our job, we then provide you a data set where you can use common data science tools against that data to extract things that are more usable building blocks to go and solve real-world problems. So extract roads, extract buildings, find different land cover types. For us, we're measuring biomass, we're measuring soil moisture. I'll show a little bit of what that looks like. And with these building blocks, you can go and then solve real-world problems in the industries where we work. So let me just walk through one example of what Planet's doing with data fusion. So we have this fusion monitoring product. And this product, the ingredients that go into it include our homegrown PlanetScope data, which is the SuperDove data that we scan every day. We also use ESA data from Sentinel-2, Sentinel-1, Sentinel-3. We have some NASA data from Landsat, MODIS, VIIRS. All of these data products, some that know satellites, you know what that is. If you're not into satellites, which I don't expect you have to be, we use some of it to get good imagery. We use some of it to get good infrared signal. We use other parts of the spectrum to eliminate atmospheric effects. When you take a picture trying to look through the atmosphere, it's really hard to know exactly what's happening on the ground. And so with sensor fusion, we can use each of these sensors to do what it does best. So we have to do 4 major steps in order to make fusion usable. First, we need to make sure all these sensors are harmonized radiometrically, which means that each of their kind of spectral signatures are calibrated to a common state. We use CSTEM, which is CubeSat-enabled spatiotemporal enhancement method, which one of our scientists developed himself, and this does some really excellent radiometric harmonization. And you can see the results in the graphs. On the left, that's like the raw data coming in. On the right, you can see really good correlation between the Planet Fusion data and third-party radiometric targets. We also have to do geometric harmonization. So you can imagine these satellites going around the Earth at 8 kilometers a second, 500 kilometers up. And what we have to do when we're imaging every day is make sure that every single pixel, every single 3-meter pixel on the ground, lines up with the pixel from the day before that, the day before that. This is a massively hard challenge. It's hard enough just being a little tiny satellite in space, going that fast, looking that far away to even know where on Earth you're looking. So taking those pixels, lining them up, so that as I do an analysis through time, we have this stack of imagery, and I'm going to see exact values in the exact same place day over day over day. There's also this pesky thing that likes to be around Earth called clouds. And when you get into satellite imagery, you don't realize just how cloudy our planet is, although today you might have a deep appreciation for that. And so clouds look an awful lot like snow. They look an awful lot like, I don't know, other white things on the Earth. And so one of the unique things that we do in our Fusion product is we're looking at the full time series. So we understand, what this place looked like yesterday, what this place looked like 2 days ago. And that gives us not 100% accuracy, but it gives us a better chance of understanding cloud versus snow versus some other white thing on Earth. And then last but not least, we fill in the gaps. So with those clouds, with orbital dynamics, there's just reasons why you can't necessarily image the entire Earth fully, completely. And so places where there's clouds, places where there's, gaps in the coverage, we want to make sure that we do good predictive analysis or good predictive estimation of what to see in any given place so that we then have this full, complete coverage of the Earth. So if we do those 4 things really well, we end up with a really nice, clean, analysis-ready data set. So this is a video that will show kind of a full year of data. And you can imagine the raw inputs here. They're cloudy. You see a bunch of seams. You see a bunch of gaps. But when we run it through our Fusion algorithm, we end up with this nice, clean, no gaps, no jumps in time, just a real easy-to-analyze data product for our customers. Now, this is a beautiful movie. I'm kind of a satellite guy, so I really like to look at these images. But it also kind of gives you a bit of the wrong idea of the real value of this data as data, right? So if you're not a satellite person, if you're not into geospatial data, this data set allows you to bring tools of just standard data science, run analysis on these pixels to see how the world is changing through time. So here's another look at that same data set, but now I'm looking at it as a single value through time, and I'm comparing that value to on-the-ground in situ sensors to see how this correlates. And you can see our Fusion-derived NDVI, which is just vegetative health index, right? So you can see the health of this crop moving through time, and that kind of faint dotted line is an in situ sensor on the ground in the field measuring the same characteristic. And so we have 150 satellites in space collecting a whole bunch of data. We're fusing that with Sentinel data. We're fusing that with Landsat data. We end up with this well-harmonized stack of fused sensor data. And then we're comparing that to a sensor completely disconnected, stuck into the ground in a field. and we end up with a correlation like this. Just a tremendous validation of the work that we do. So we have a lot of big questions to answer. We want to go and learn so much more about what fusion can do. But in the meantime, we're bringing out a lot of kind of interesting products. Our first set of planetary variables that was built by our team here locally in Haarlem. And they have soil water content, land surface temperature, biomass proxy. These are physical measurements of characteristics on the ground. And they derive this from passive microwave, radar, and optical data, all fused together from various missions, including Planet. And we can deliver these physical characteristics on what exists on the ground as we measure them from hundreds of kilometers up in space. So for us, ML is the tool and the capability that allows us to go beyond imagery, beyond just collecting a massive archive of imagery data, and instead making it something that we can analyze, something we can use to really unlock all the insights that exist. It's ML with computer vision, lots of other tools that our team uses in order to extract these things and make a real difference at a global scale, both in sustainability, security, as well as just hopefully making our planet a better place. So with that, thank you very much.
Thank you, Jim. This stuff must leave you in awe of our planet. Very beautiful planet. Okay, let's take maybe one question if we have any. Maybe someone from this side of the room. Okay. Mic runner, go ahead. Yeah, perfect. And make sure to hold the mic close to your mouth.
Oh, thanks for the talk. I'm just curious, you systematically underpredict the NDVI, I think for that plot. I'm curious what you think, during summer only, right? So what do you suspect was happening?
I'm sorry, I missed the question.
So the NDVI plot you just plotted with your prediction, it over-predicted systematically over summer, from, I think, June to August, underpredicts this plant health indexes, right? So I'm just curious what you think the fusion will do that's different that will make it better.
Yeah, so on that plot, there's a lot going on. So there were some direct measurements that were under the in situ sensor, but then the fusion line actually tracked the in situ sensor quite well. I mean, maybe some discrepancies, but I would say it was within the error band of both the sensor as well as what we would expect to see in fusion. But the raw sensor data were the individual dots that sat underneath it, and those were the ones that tended to be low, and those were top of atmosphere measurements, which is why it was systematically low, because the atmospheric effects kept it below the line.
Okay, maybe we try one more. Can someone ask like a 30-second question? How about back there? And let's see if we can do a 1-minute answer. Be efficient with our time.
All right.
Hi, thank you for the presentation.
Yeah.
I was wondering for the gap filling approach, what is the method you use? Are you using the last seen observation within the temporal component, or what is it?
The approach for which part exactly?
For the gap filling approach.
Oh, for the gap filling? I do not know that one. I can point you to Rasmus Hubert, who's he built CSTEM, which is kind of the underlying model, and I don't know exactly which model he builds that on top of. It's published work though, so.
Okay, thank you.
Yeah.
Awesome, Jim. Well, thank you so much. This has been amazing.
Absolutely.
Let's hear it for Jim. Thank you.